गुड आफ्टरनून बच्चों। कल आपको पढ़ा रहे थे फोटोमीटर्स के बारे में, उसी को कंटिन्यू करते हैं। हमको कुछ एसोसिएटेड ऑप्टिक्स चाहिए होते हैं फोटोमीटर्स से संबंधित। इन कलरीमीटर्स एंड स्पेक्ट्रोफोटोमीटर्स सिंपल लेंसेज आर यूज्ड टू फोकस और collimate the light beams. In special types of spectrophotometers, front surface mirrors are used to reduce the energy loss. The surfaces of these mirrors are coated with thin film of magnesium fluoride to reduce the light scattering. Then the next part of it is the photodetectors. These devices convert light energy into electrical energy, which can be measured by a galvanometer. The most common of these devices are the photocells, the barrier layer cells. These cells are composed of an iron black plate coated with a layer of crystalline selenium or cadmium on one surface, the front active layer. This light sensitive material is then turned coated with the thin transparent film of gold or copper. The back side of the metal plate is connected to a galvanometer. Light passing through the transparent film sets up a flow of electrons in one direction. This develops potential difference between the two poles of the cell and causes a current to flow which is proportional to the concentration of the solution and detected by a galvanometer. Phototubes are either evacuated or glass-filled tubes similar in appearance to radio tubes. These are constructed of a negatively charged cathode and a wire-like positively charged anode. The cathode is coated with a photo-emission substance such as cesium oxide. When light strikes this layer, according to the proportion of the incident light, electrons are emitted and these jump the vacuum over the anode. The generated current in the external circuit is after amplification by an amplifier circuit can be determined galvanometrically. An advantage of phototubes is that they may be obtained with wide ultraviolet and infrared sensitivity, which is not the case with the photovoltaic cells. A further development of the photomissive tube is the photomultiplier. In this, great sensitivity is attained by using a number of elements within the phototube acting in series. It can measure light intensities about 200 times weaker than the ordinary phototube. Then the next part of it is the readout devices. A galvanometer is used to detect and measure electrical current produced by the photodetectors. It contains a flat suspended coil in the plane between the poles of a permanent magnet. When electrical current passes through it, a magnetic field sets up 90 degrees away from the permanent magnet poles. In trying to set its lines of force in line with those of the magnet, the coil turns as far as the magnetic forces can twist the wire. The readout display is in the terms of percent transmittance, that is optical density OD in milligrams per deciliters usually, and the concentration of a component in the specimen. The specifications of some of the commonly used photometers and spectrophotometers are as follows. The ERMA photoelectric colorimeter, it has a detector of one selenium photocell, a filter glass of 420, 470, 530, 620 and 660 nanometers. It has a round cuvette with 12 mm diameter and the minimum quantity required for the reading is near about 3 ml. The light source of it is a tungsten bulb of 6 volts and 3 amperes. The scale transmittance is 0 to 100 in 100 divisions and the weight is near about 6.3 kgs. Then comes the Spectronic 20 spectrophotometer. It has a wavelength range of 340 nanometers to 600 nanometers and the infrared region of around 600 to 950 nanometers and a wide range phototube of about 400 to 700 nanometers. It has a spectral slit width of near about 20 nanometers with wavelength accuracy of 2.5 nanometers. The photometric range is 0% transmittance to 100% transmittance, that is 0 amperes to 2.0 amperes. The photometric readability is near about 0.5 of the percent transmittance. The cuvette is usually round type glass cuvette with minimum quantity required for reading near about 3.5 milliliters. Then comes the Spectronic spectrophotometer. It has a wavelength of about 340 to 960 nanometers. It has a bandwidth better than 10 nanometers, a wavelength accuracy of better than plus minus 5 nanometers, and the measurement accuracy is 0.005. The sample holder has about 10 millimeters rectangular cuvette. The detector is of high quality silicon photodiode of uniform spectral response throughout the range of 340 to 960 nanometers, and the grating is of 600 lines per millimeter. The operation of a single cell photometer is mainly that we put on the main switch, then place a proper filter, place a cuvette filled with distilled water, put on the main light source, keep it on for 10 minutes before taking the reading. By using the control knob, turn the galvanometric pointer to 100% transmittance, replace the distilled water cuvette by another similar cuvette containing a colored solution, record the readings either in terms of optical density or percent transmittance. If necessary, use the chart to convert the percent transmittance reading into the OD, that is the optical density. Place the cuvette containing the distilled water and bring the galvanometric pointer back to the 0% transmittance. Some care and maintenance is also required for it, that is, always put on the plastic cover on the photometer when it is not in use. Before putting the photometer on, put a filter and cuvette filled with distilled water in their respective positions, and many of the biochemistry experiments are based on photometry. Hence, the use of photometer is very carefully done in the pathology labs. Check the sensitivity of the galvanometer occasionally by using a standard dichromate solution. Now, the laboratory tests are based usually on colorimetry and photometry. The laboratory tests based on colorimetry and photometry can be divided into two categories: endpoint reactions, that is fixed time methods, and the second one is the rate of reaction methods, that is continuous monitoring methods. The endpoint reaction methods are carried out under specific experimental conditions by maintaining constant temperature, pH, and the reaction period. At the end of the procedure, the reaction between an analyte in the specimen and a specific reagent or reagents results in the formation of a colored complex and turbidity or certain components such as NAD or NADH. The concentrations of the specific analyte under the test can be determined by determining the intensity of the end product. The endpoint reaction method can be further divided into following two types: qualitative tests and quantitative tests. The qualitative tests give idea only about the presence or absence of a specific analyte in the specimen. For example, Benedict's qualitative test is used for the detection of urine in the sugar. Fauchet test, that is used for the detection of bile pigments in the urine. Now coming on to the quantitative methods, these tests gives idea about the exact concentration of a specific analyte in the specimen. These methods can be of two types: multi-step methods and monostep methods. The multi-step methods, the procedure of it is followed through several steps by using many reagents. Most of these methods are time consuming and non-specific. For example, blood sugar determination by Fallin-Bu's method and the uric acid determination by Henry Caraway's method. The monostep method consists of a procedure of only one step. In the specified amount of the reagent, specified quantity of a specimen is added and mixed well. The intensity of the end product is produced under specific experimental conditions. It is then measured by using a photometer or a spectrophotometer or an nephelometer. The examples of such type of reaction are the enzymatic endpoint reactions methods for the determination, such as glucose oxidase methods, uric acid in the uricase methods, etc. Biurate and the BCD test for the determination of serum total proteins and albumin respectively. Turbidimetric determinations for the determination of urinary and CSF proteins. Most of the monostep methods are accurate, precise, sensitive and specific. These methods can be easily adapted on various autoanalyzers. A qualitative test is reliable only if it is performed by using the following requirements. For accurate work, appropriate primary standards should be included with each batch of the determinations. Variation in the chemical reaction and in instrument behavior combine to cause variability in the absorbance produced from one batch to another. The standard reading, however, compensates the variability in the readings when the final results or concentrations of analyte in the specimen are calculated. With each batch of determination, it is also necessary to include a reagent blank, particularly if the reagent is colored. The reagent blank is used to eliminate intensity of the reagent from the intensity of the end product, that is, the colored complex formed at the end of the procedure. A reagent blank is not necessary if intensity of a reagent corresponds to zero optical density. A specimen blank is also used if a specimen is hemolyzed or lipemic. A specific specimen blank reagent is used to prepare a specimen blank. A specimen reagent blank is compared as follows by eliminating an active chemical from the reagent used in the test. In the case of glucose oxidase reagent, glucose oxidase and peroxidase are eliminated from the reagent. For the determination of hemoglobin, a cyanomethyloglobulin secondary standard is used. Similarly, for the determination of bilirubin, methyl red and cobalt nitrate are used as secondary standards. Now coming on to the next methods that are used, we have another principle which involves fluorimetry. Molecules at rest in the ground state, existing in the singlet state, and when energy is supplied in the form of high energy photons from a suitable light source, the singlet state is elevated to high energy state or levels called as excited singlet levels. Now we have certain other examples of it, such as pH ion selective potentiometry. When a metal is immersed in a solution of its own salt, the metal begins to dissolve by releasing electrons and will be more negatively charged relative to the solution surface. For example, if zinc rod is immersed in a solution of zinc sulfate, the release of electrons by zinc metal ion amounts to the oxidation occurring on its surface, and the zinc metal or electrode can be characterized as the anode. The zinc sulfate system presents a half cell. If this half cell, that is the zinc sulfate, is brought in contact with another half cell of copper and copper sulfate through a salt bridge, the electrons from the zinc electrode will flow to the copper electrode and the following reactions will take place. The copper rod represents cathode in the case, and deposition of the copper on the copper rod takes place. The salt bridge connecting the zinc and copper electrode system prevents mixing of the two solutions and free movements of the ions between two components to maintain the electrical neutrality. This type of electrochemical cell is called as a galvanic cell, and the single vertical lines indicate phase boundaries, that is electrode and the electrolyte interference, and the double bars represent all the salt bridge. Potentiometry involves the use of galvanic cells with the measurement of a potential of an electrode without current flow. The commonest application of potentiometry is the pH electrodes, ion selective and gas sensing electrodes. The hydrogen ion concentration or pH is a measure of the acidity or alkalinity of a solution. It is the hydrogen ions in the hydrogen concentration of the solution in moles per liter. At given temperature in an aqueous solution, the product of the hydrogen ion concentrations and the hydroxyl ion concentration is constant. Hence, measure of hydrogen ion concentration gives measure of the hydroxyl ions concentration also. At a temperature of 22 degrees Celsius, this product conveniently happens to be exactly 10 to the power minus 14 expressed in gram molecules per liter. The pH scale is introduced to avoid awkward small numbers. The pH of a solution is defined as a negative logarithm of the hydrogen ion concentration in aqueous solutions. If the solution is described as pH 6, its hydrogen ion concentration is 10 to the power minus 6 and its hydroxyl ion concentration is 10 to the power minus 8 at room temperature. The value of using pH can be seen in the case of human blood, which has an extremely low hydrogen ion concentration. The scale of pH meter is normally taken as extending from 0 to 14 pH. An acid solution has a pH value less than 7.0 and a basic solution has a pH value greater than 7.0. A neutral solution has a pH value of 7.0 and a change of 1 pH unit corresponds to a 10-fold change of hydrogen ion concentration of the solution. The most reliable and convenient method for measuring pH is by the use of a pH meter. It measures the EMF of a concentration cell formed from a reference electrode, the test solution, and a glass electrode expressed as when a pair of electrodes or a combined electrode or glass electrode and a calomel electrode is dipped in an aqueous solution, a potential is developed across the thin glass of the bulb of the glass electrode. The EMF of the complete cell formed by the linking of these two electrodes is the EMF, that is the total of the EMF of the reference and of the EMF of the glass. The E reference is the potential of the stable calomel electrode, which is at normal temperature of plus 0.250 volts. The resultant small EMF can be recorded potentiometrically by using vacuum tube amplifier. Variations of the pH with the electrodes may be recorded directly on the potentiometer scale graduated to read the pH directly. The important components of a pH meter are a glass electrode, that is, it consists of a very thin bulb about 0.1 millimeters thick blown onto hard glass tube of high resistance. The bulb contains 0.1 mole per liter HCl connected to a platinum wire via a silver-silver chloride combination. The calomel electrode, it consists of a glass tube containing saturated potassium chloride connected to a platinum wire through mercurous chloride paste. Buffers are used to prepare the buffered substrates which are required for the determination of enzymes in various specimens. The phosphate buffer is used for the preparation of phosphate buffer substrate of SGOT and SGPT enzymes by the endpoint reactions. The glass electrode of a pH meter is a kind of ion selective electrode, that is ISE, that is sensitive to hydrogen ions. Similar Photopotentioelectrodes have been developed which are responsible for other ions such as sodium, calcium, lithium, etc. Glass is the active material within the pH electrode, but modified aluminosilicate glasses may be used to produce a variety of monovalent cation responsive for electrodes for the determination of sodium, potassium, calcium, lithium ions in samples using appropriate standards and calibrators. Insoluble inorganic salts such as silver sulfide may be used to produce electrodes responsive for copper, lead and cadmium. The ion selective membrane which separates the solution on the left side from the solution of the right side in reference electrode is that the test sample and the membrane, it consists of two solutions in the reference electrode. When the ion selective electrode is dipped in the test solution, a positive membrane potential develops. It is due to the higher activity of the diffusible cations in the solution that the solution or the reference electrode solution on the left hand side where the cation activity is high and the cations are bound to the membrane surface by specific binding groups. Due to this reaction, the membrane becomes positively charged. This causes a dissociation of the cations from the other side of the membrane into the solution on the right hand side. This side of the solution becomes positively charged with respect to the solution on the left hand side. The process proceeds until an equilibrium is established. This occurs when the electrical potential difference across the membrane matches the difference in activity of the diffusible ions of the two sides of the membrane. The membrane potential is directly proportional to the logarithm of the activity of the diffusible ions in the test solution. The membrane electrodes may be flat, bulb shaped, needle type, capillary type or flow through type. These electrodes can be classified as glass electrodes, number 2 as solid state electrodes, number 3 as liquid ion exchange electrodes, number 4 as gas electrodes and number 5 as enzyme electrodes. The solid state membranes can be homogeneous and consist of single crystals or heterogeneous membrane that contains an active substrate embedded in an inert matrix. For example, electrodes for the determination of chloride in silver chloride and in cupric selenite. The second type, that is the ion exchange electrodes. The liquid ion exchange membrane consists of an inert solvent in which an ion selective carrier substance is dissolved. The solvent and the carrier should be insoluble in water. The membrane solution can be separated from the test solution by means of a collodion membrane. The inner solvent and the ion selective carrier are embedded in the matrix of polyvinyl chloride. Selective membranes can be made by dissolving the antivitic valinomycin in a suitable solvent. Valinomycin is a neutral carrier that binds the potassium ions in the center of a ring of oxygen atom. This membrane is highly selective for the determination of potassium ions in a sample. The next type is glass electrodes. These are designed for the measurement of specific gases in the blood specimen. For example, determination of PCO2 in blood, it is based on potentiometric measurements using a pH glass electrode. The electrode used for PO2 determination is based on amphoteric measurement using a polarized platinum cathode. Now, what is amperometry? This technique is based on measurement of current flowing through an electrochemical cell when a constant potential is applied to the electrodes. For example, the PO2 electrodes. The PO2 electrode is a complete electrochemical cell consisting of a small platinum cathode and a silver to silver chloride anode and potassium chloride in phosphate buffer. The platinum cathode is covered by a thin film of electrolyte. It is separated from the test solution by a polypropylene membrane which is permeable to gas. When no oxygen is present in the test solution, the cathode is polarized and the current is almost zero. When the PO2 electrode is dipped in a test solution, in the presence of oxygen in a sample, a current develops due to the diffusion of oxygen from the test solution through the membrane to the cathodes where it gets reduced. The current is directly proportional to the PO2 in the test solution. The next technique is known as Cowlimetry. This technique is used to determine chloride ions in the specimen. Most Cowlimeters are based on the principle of constant current Cowlimetry. The Cowlimeter consists of a pair of silver generation electrodes and another pair of silver electrodes to amperometrically detect the endpoints of titration. The sample is diluted with a mixture consisting of nitric acid, acetic acid, gelatin and thymol blue. A timer is activated as soon as the sample is titrated with silver ions, generally at the silver anode by application of a fixed potential of 1 to 2 volts. The silver ions generated at the anode react with chloride ions in the sample to form insoluble silver chloride. The nitric acid provides protons to facilitate the cathode reaction. The acetic acid decreases the polarity of the solution and ensures that silver chloride remains insoluble. The gelatin improves the reproducibility of titration. Thymol blue prevents microbial growth and serves as a visual indicator. The detection of the endpoint of titration is achieved by the other pair of silver electrodes to which a constant potential of 0.25 volts is applied. As soon all the chloride ions in the sample have reacted with the silver ions, the subsequent generation of silver ions results in an increase in the current in the amphoteric electrode. The increase in current triggers a relay mechanism. It stops the timer and the generation of silver by silver generator electrodes. Next method is osmometry. It is a technique for measuring the concentration of solute particles in a specimen. The dissolved solutes increase the osmotic pressure and boiling point of the solution or the specimen and decreases the vapor pressure and the freezing point of the solution or the specimen. These qualitative properties of a solution are directly related to the number of solute particles per mass of the solvent. Any of the four properties could be used as a basis for the measurement of osmolarity. The freezing point depression is most commonly used to determine the concentration of osmotically active particles in the specimen. Since osmolarity determination by this method is simple and convenient, a depression in the freezing point of a solution of 0.00186 below than that of water taken at 0 degrees Celsius is equivalent to 1 milliosmoles of osmotic activity per liter. Water distillation apparatus is used to prepare the distilled water by using the tap water. It is practically free from the interfering ions. The components usually are the still made from stainless steel or heavy gauge brass sheet and a steam condenser tube from the stainless steel. Heating coils may be fitted with ejection device in the event of failure of water supply, and there is an inlet, overflow pipe, lid and an outlet. The tap water in the still gets heated by the heating coils. When it boils, the vapors are formed. These vapors are collected in the condenser and are cooled by the circulated tap water. The condensed distilled water is free from the interfering ions and collected through the outlet. The inlet is connected to the tap by means of a rubber tubing and the tap water is introduced into the still. The water level in the still is checked by the overflow pipe. This ensures sufficient water over the heating coils. By putting on the electrical connection, the coils are heated. When water boils, the vapors are collected in the condenser and distilled water trickles through the outlet. It should be collected in a polyethylene container, and after the collection of distilled water, the lid of the container should be closed tightly. It is necessary to ensure before heating the coils that insufficient water is introduced in the still to maintain the water level above the coils. The rate of preparation of distilled water depends on the type of the apparatus used, and the yield of the distilled water ranges from 4 to 8 liters per hour. The collected distilled water tends to become acidic due to the exposure to air by the dissolution of carbon dioxide, hence the lid of the container should be closed tightly. The distilled water obtained from this type of apparatus may not be suitable for the determination of electrolytes, though it is suitable for all other biochemical tests. It may contain traces of sodium and chloride ions also. The glass distilled water is prepared by using a distillation apparatus made up of glass. The distillation is carried out by heating tap water in a glass flask with electrical elements. The distilled water thus obtained by using this apparatus is called glass distilled water, and this does not contain the interfering substances, and it is used for electrolyte determinations. Then we have deionizers. The specific features of it are water of highest purity can be obtained by using deionizers. These are used in chemical, pharmaceutical and research laboratories. The general features of it is a body of universal deionizer consisting of a number of cylindrical vessels connected in a series and charged with high grade purified cations and anion polyelectrolyte resins. It contains two separate flow circuits, a water flow circuit for deionization and a regenerate flow circuit for the regeneration of the resins. While one flow circuit is on, the other remains off. The water purity monitoring device consists and measures the conductivity of the outflowing deionized water. It contains the conductivity bridge and a meter scaled in a plastic container and specially designed conductivity cells. Besides, these devices are fitted with some tests of special effect filters for adsorption of the dissolved organics and micron-sized organisms. The advantages of it are the deionization of water does not require heating, and hence there is no fuel or electrical consumption. The instrument is just connected to a water tap and the pure deionized water can be obtained. The deionized water is suitable for the electrolyte determinations. The distilled water should be free from the interfering substances or ions such as sodium, calcium and chlorides. The appearance of turbidity by the addition of 2 to 3 drops of concentrated nitric acid and silver nitrate indicate the presence of interfering ions. Biosensors are also defined as a device in which an immobilized biological or biochemical component interacts with the analyte to produce a signal via an appropriate transducer proportional to the quantity of the analyte. Biosensors are particularly used to determine a specific component in the specimen in emergency laboratories and all the patient bedside or in satellite laboratories. The biosensors are useful to determine components in the sample such as glucose, urea, cholesterol, nitrate, penicillin, etc. When a sample is introduced to a biosensor, the glucose oxidase or the biocatalyst in the biosensor acts on the glucose, and the various ways for determination of the glucose by using the above is that the rate of consumption of oxygen can be measured by its reduction at platinum cathode or polarized at minus 0.6 volts versus the standard calomel electrode. The rate of production of the product H2O2 can be measured by its oxidation at the platinum electrode polarized at 0.7 volts versus the standard calomel electrode. The rate of production of gluconic acid is measured by using a pH electrode with associated decrease in the pH. The oxygen electrode measures the rate of oxygen uptake, and this can be related to the cholesterol concentration of the sample. Thank you.